Hi, what I have here on the workbench today is a Brymen BM788BT multimeter. It is a 60,000 counts meter with Bluetooth connectivity. To be very honest, I have been looking at Brymen's meters for a while now and have always wanted to get my hands on one, especially Dave Jones at EEV Blog seems to be swearing by it. Of course, he also sells Brymen meters with the EEV Blog exclusive model numbers. Anyway, so I reached out to one of Brymen's distributors, LowZ, in the Netherlands, and asked them if I could review one of their latest Brymen meters, and they kindly sent me this BM788BT. So if you like what you see after watching this video, please be sure to check them out following the link in the video description below. Now, words of caution, due to the recent tariff changes, importing the meter into the United States is actually surprisingly expensive. The duty turned out to be 40%. Who knew? Anyway, I thought I'd share that with you. Of course, now I have skin in the game. One of the primary reasons I wanted to review this meter is because, as far as professional-grade multimeters go, Brymen is probably one of the best alternatives to Fluke, and it is considerably cheaper. So I do want to take an independent view of just how good a Brymen meter is. The BM788BT is a very well-spec'd true RMS meter. And in the series you can see here, we also have the 789, 785. All these are fairly comparable in terms of the capabilities. Of course, the 788 has Bluetooth, and there are some minor variations between these three meters, but largely speaking, their specs are fairly comparable. And you can see here, we have essentially a very exhaustive listing of the specs in the user manual here. Of course, I'm not going to go through this with you, but I want to point out a few highlights here. And you know what? Let me actually bring in a product box so you can see the spec highlights yourself. So here is a product box. You can see here it's BM780 series. And on the back here, we have some of the highlights. And from a glance, you can see that it's very well spec'd. It has 60,000 counts. It has voltage accuracy of 0.03% plus 2 digits in low voltage ranges. And also you can see here, it has pretty fast update rate. The update rate is specified as 5 times per second, and the bar graph updates at 50 times per second. A few other features worth mentioning is that it has low impedance voltage measurement mode, or the LowZ mode. It supports AC plus DC measurements in both voltage and current ranges. It supports dual thermocouples. And of course, it has built-in Bluetooth connectivity as well. So it's definitely a very feature-rich meter. The first thing you'll notice is that the meter is heavier than most of the meters of the same size. Here I have a UNI-T UT61E Plus on the side, and you can see that they are almost identical in size, with slightly different shapes. The dial switch on the meter feels very solid. It is hard to describe, but it's precise, albeit a little bit stiff. You can still operate it with a single hand though. For example, right now I'm just using a single hand to operate it. You can see that there's no problem. It doesn't slip on the surface. Let me actually stand it up to see if we can operate with a single hand with a stand here. And by the way, you can see on the stand here, we have a sticker, and I think it's Polish. I'm guessing it means distribution here. So I guess this meter started in Taiwan, went to Poland, Netherlands, and then ended up here in my lab. Let me pull out the stand, and you can see that the stand is actually fairly sturdy. Anyway, let's put it down here. And let's see if we can operate with one hand. Yeah, no problem. But you do need to put a little bit of force, either downwards or on the meter itself, so that when you turn the switch, it doesn't move around, as otherwise you just will kind of move around on the table here. But anyway, I think that's actually not an issue. It's fairly easy to operate. By the way, you can probably tell already, for dial switches, I'm pretty picky, but I don't think I have any major issues with the switch here. I'm not sure if you remembered, but when I reviewed the UT61E Plus more than 4 years ago, I mentioned that the switch on this meter is a little bit springy than I liked, and occasionally it gets stuck between the ranges. For example, like this. Of course, right now I have to force it, but it does get stuck, for example, between the ranges. And sometimes you have to give it a little push to actually help it settle. But the dial switch here actually turned out to be very reliable. After all, I've been using this meter daily for many years. The switch design in the UT61E Plus is actually very similar to that of a Fluke. In comparison, the switch on the BM788BT is not springy at all, so I definitely like that a lot. My plan is to use the BM788BT as my daily meter from now on, so that we can evaluate the reliability and see if there's any issue that would arise in the long run. Now, while we're on the diode switch topic, the best diode switch I ever used is actually on my BK2709B. Let me actually grab that meter and show you. Anyway, here is my BK Precision 2709B. I've had this meter for a long while, and this is only a 6,000 counts meter. But anyway, so let's take a look at the range switch here. In my opinion, by the way, this is probably the best designed range switch of all meters. The sound and the feel and the precision just seems to be perfect with this range switch. Of course, the beeping sound is a little bit annoying. Anyway, the switch on the BM788BT has a different feel, but it's pretty good overall. The off position on this meter is not as traditional, as you can see, it's not towards the end. Now, I understand why Brymen chose to do it this way, as there are two voltage ranges you can see here. One is low impedance auto range, and the other is the AC and VFD range. They are probably the most frequently used ranges. So I guess the reasoning here is you only need to turn it by one notch to reach either of these ranges. The downside of this design is that when you power off the meter, you do need to pay extra attention. While I was testing this meter in the last couple of days, I had found myself left the switch in the LowZ mode a couple of times already, as it's just a habit to turn the switch all the way back down. Now, I'm sure if this is the only meter you're using, you will eventually get used to it. But since most meters are not designed this way, unfortunately, this will continue to happen. But I suppose the saving grace is it has auto power off feature. So in the grand scheme of things, leaving the meter on is probably not a big deal. Anyway, let's take a look at the probes that came with this meter. And you can see the supplied probes are absolutely top quality. Not only are these silicone wires, the tips are gold plated and you get these screw-on lantern tips. Now, for our test today, probably we'll be taking these off because these are typically used if you have to insert them into banana jacks. And here's a close-up of the tips. You can see that they're pretty sharp and also they're gold plated. No problem at all. Because the meter is Cat 4 rated, you also get these shrouds you can put on. Let's try that. And that makes it Cat 4 compliant. But anyway, for today's test, we're not going to use these. I should mention that the meter has input jack detection feature, which means it will warn you of the wrong jack insertion given the selected range. Let me actually demonstrate that. Now let's just say if you're in voltage measurement mode, for example, you came back from current measurement mode and you forgot your probe in the current jack. Let's just see what happens. And you can see that you hear this audible warning that you're in the wrong socket. And similarly, let's say if you're in the microamp range and you inserted your probe into the amp jack, again, it will warn you because potentially you're going to overrange and blow the fuse. Probe detection is a great feature. Many high-end meters support that. My BK2709B also has this feature as well. The plus side is that it greatly reduces the chance of you accidentally blowing the fuses while trying to measure voltage while the probes are in the current jack, as those HBC or high breaking current fuses are not exactly cheap. But the downside is that it uses split sockets. We'll have to take a look at that later on in a teardown. Now, these sockets are not as robust as those single-piece sockets, and the detection circuit could also malfunction if you have contamination in the sockets. With the basics out of the way, let's actually do some measurements. And by the way, you can see the display quality is excellent. The letters are big and also the viewing angle is very wide. You can see we have no problem seeing the display from various angles. Now let me turn on the backlight. Wow, you can see it is actually very bright. Now, some people might prefer different colors, different brightness, but for me, this is actually great. I like that. Now, I do have a comment here. You can see the backlight is actually a secondary function of the select button, so you have to long press it to activate the backlight. If I were designing this meter, I would probably put the backlight function as a secondary function on this crest button because this one currently is only for crest only. And this is because the select button is used very often to cycle through the secondary functions, and when turning on and off backlight, if you don't hold the button long enough, it will change the secondary selection instead. And you have to press it multiple times to cycle through and get back to where you were. So I would make the select button a dedicated button instead, and put a backlight function on some other buttons. For example, this crest, currently it doesn't have a secondary function. Anyway, that's just my personal preference. I don't think it's a major issue. Speaking of the select button, the last selection will be saved as your power on default. Actually, let me show you that. So for example, right now we are in AC measurement mode. Let's actually change it to, let's see, VFD. You can see the VFD here. And let's turn it off. And let's turn it back on. And now you can see the VFD measurement retained. So this behavior is quite different from other meters I have used. Most meters would reset to the default selection when you power cycle it. If you're not expecting this behavior, you could be surprised. But this is actually a good feature in my opinion. All right, let's actually take a look at the AC measurements first. The AC measurement is true RMS, obviously. And here we have a UTG-1042X, that's a function generator. I'm generating a sinusoidal at 1 volt RMS with a frequency of 60 Hertz. And you can see the measured result on the Brymen and also the UT8806, which is a 6.5-digit multimeter. They are roughly the same. Of course, the last digit is slightly different, but that is well within the measurement tolerance. Let me change the output voltage here. So let's do 2 volts. And you can see that they largely agree, of course. Although there are some discrepancy between this meter and the 6.5-digit meter, and I can tell you that this is definitely within the tolerance because if you look at the manual here, it is actually 0.5% plus 30 digits for 50 Hertz to 60 Hertz. So anyway, so if you do the calculation, that is definitely within the range. Yeah, let's do 3 volts. No issues. 4. 5, 6, 7. And for this function generator, I think that's the highest I can go. I do want to see how it handles higher frequencies here. So let's actually turn it back down to 1 volt. And what I'm going to do is I'm going to adjust the frequency here. So let's do frequency. And let's first do 100 Hertz. I don't think that's going to be a problem. You can see that both meters roughly agree. So let's do 1 kilohertz. And you can see no problems. So let's actually do 10 kilohertz. Again, you can see the readings are very comparable. And now let's do 100 kilohertz, which is the limit. And you can see both of these meters are essentially agreeing with each other. Of course, the readings are higher, and that's not a problem of the meter, and I think that's a variance of the function generator output. And let's try to increase the frequency a little bit more and see what the behavior is. Remember, this is actually 100 kilohertz. That's the bandwidth specified. So let's go 110. Yeah, you can see we started seeing some deviation between these two meters now, 120. So indeed, this meter is probably only good for up to 100 kilohertz. Actually, let's now measure mains voltage. And now I have connected the output of the variac to both of these meters, and let's actually ramp up the voltage, and let's see how accurate the BM788BT is. So let's start ramping up the voltage. So right now we're at roughly 12.57 volts, and you can see the voltage largely agree with each other. Of course, the UT8806E is for precision, it's not for speed. So let's ramp it up. Let's do maybe 60 volts, and you will see as we pass 60 volts, at some point you will lose a digit because this is a 60,000 counts meter. Right now you can see the measurement is largely in agreement. So it does seem we have quite a bit of margin here. So roughly the cutover is around 65 volts. And I don't think we have any warning after we increase the voltage. You can see we don't have any warning. Some meters, for example, in AC voltage mode, after about 50 volts, 60 volts, it will start showing you a warning. But this meter doesn't have that. And the highest is 147. And right now we're at the top of the variac output. And you can see the output is more or less what we expected. Remember, in AC measurement mode, the accuracy of this BM788BT is not as high as in DC measurement mode. And let me just quickly show you the update rate of the bar graph. We'll take a look at that in detail a little bit later. Brymen also has electric field or live wire detection capability. So let me demonstrate that. Let me press on the EF. And you can see right now we're actually in high sensitivity mode, even though we're only at 13 volts. You can see that when I'm approaching the wire, it actually detects that electric field. So of course we can lower the sensitivity here. by pressing it again. And now, of course, we don't detect that, but let me ramp up the voltage here. 60 volts. And you can see that we are able to detect that. Of course, let's turn it to the mains voltage here. And let's try it. Yeah, you can see that it works very well. And while in the EF mode, you can also use the negative lead to actually detect live wire. For example, let me demonstrate. You can see that this is live wire, this is not. So this is definitely very convenient. Of course, Brymen can also measure line frequencies. Now, you do that by pressing the button with the Hertz symbol on it. Now you can see the measured frequency here. Of course, in North America, we're 60 Hertz. The maximum frequency can be measured actually depends on the range and the measurement type. For current frequency measurement, it's up to 5 kHz. For VFD frequency measurements, it's up to 400 Hz. And for voltage, it depends on the voltage range, and it's between 5 kHz and 50 kHz. Brymen actually has another dedicated range for logical frequency measurement. And in this case, it's through a different selection. Let's take a look. So for logic frequency measurement, it's actually a secondary function of the millivolt range you can see here. The maximum frequency in this case can be measured is spec'd as 1 MHz with square wave input greater than 3 volts. Let's take a look. And here on the function generator, you can see I'm currently outputting a signal with 1 kHz, 5 volts RMS, and let's actually change it to the range here. And now its frequency, you can see we're at 1 kHz. So let's increase the frequency here. 10 kHz, no problem. And let's go to 100 kHz. Yeah, no issues. Let's go to 1 MHz. And you can see we are at the specified limits, 1 MHz. And let me increase it a little bit more. 1.1, 2, yeah, it's still able to, 3, 4, so there's quite a bit of margin built in. So let's see here. That's 2 MHz, no problem. How about 3? No problem. 4, 5, 6, 7. Yeah, so you can see definitely we can push quite a bit. Of course, it is also amplitude dependent. So let's actually reduce the amplitude to 3 volts RMS because that's specified. And you can see, yeah, we're not able to measure 6 MHz. We can come back here. Let's adjust the frequency here. Let's go down to 3 MHz. So you can see that the maximum measurable frequency is obviously dependent on the input signal's amplitude as well. But we have definitely quite a bit margin built in. You can also do automatic voltage measurements with the low impedance mode, which is the LowZ mode. And one of the benefits of this, of course, is that you can get rid of the ghost voltage. And because this is auto mode, the input voltage has to be greater than 1 volt. And in this LowZ mode, let's actually measure a battery. And that is important. Sometimes the battery is flat, but because of the internal resistance is high and also the high input impedance of the meter, you wouldn't be able to tell whether or not the battery truly can deliver the voltage. But in this case, because we have a load resistor on it, you can see we are actually measuring the true voltage of a battery. So in this case, it is very good. And typically, you want to use the LowZ mode when doing such measurements. The LowZ mode dynamically changes the input impedance, depends on the current measurement voltage. The initial impedance is at 2.1 kilo ohms. This means if you are measuring the maximum rated voltage, you would have a peak current of over 600 milliamps for a brief moment, before the internal resistance is adjusted to the maximum 670K. The meter itself is designed to handle that large inrush current. So this feature is actually very useful because you can use this LowZ mode to safely discharge capacitors with voltages up to 1000 volts. You do need to be careful with the LowZ mode though. Sometimes if you're not careful, you could get the wrong reading. For example, right now we have the function generator generating a 100 Hz 5 volts RMS voltage. So let's actually take a look at what is measured by the LowZ mode. And you can see we're actually only getting 4.9 volts. And this could be attributed to a couple of factors, but mainly because of the input impedance is essentially loading the function generator's output. Of course, one of the main selling points of the BM788BT is its Bluetooth connectivity. So let's actually take a look at that. So here I have downloaded the phone app. Of course, I have already paired it up with the meter here. In theory, I should just be able to enable the Bluetooth on the meter and it should be connected. So let's try it. Now I have turned on Bluetooth. It appears it does take some time for the phone to register. Yep, eventually you can see that we are actually showing the same range as what is on the meter here. And of course, if I turn the dial here, I would expect, yep, it changes on the phone as well. You can see that essentially the phone reflects what is being set on the meter here. Very good. And of course, if we change range, yep, it changes on the phone as well. So here is another reason why you don't want to have the off position in the middle of the switch here. Because if I were to, for example, switch to Auto V, LowZ mode, I would have to turn off the meter first, and that actually would reset the Bluetooth connection. Anyway, so this is just something minor, but definitely something that I have noticed. So let's take a look at what else we have with this Bluetooth app. So you can see here, we actually don't have a whole lot. We have dashboard, record. Oh, by the way, the record here potentially is going to be useful. So let's actually start that. Let me show you. So now what this does is if you press hold, so it should record the current reading from the meter. So you can see here, that is what we recorded. And of course, if we change to a different range, I can do the same thing here as well. You can see that the current reading is actually recorded. Very good. And of course, you can also save the results to a file. So let's try one more time. You can see that the latest value is recorded. So let's take a look at a few other functions here. So let me go back here. No, we don't want to save it. And you could save it. If you did save it, you can actually review the numbers you saved earlier. So let's go back. And the battery, I don't think this is actually meant for this meter. Let's actually take a look. Yep, you can see that it is not for this meter. So then we have files. These are the stored files. And about, let's see here. So this is a version number, let's see, of the app. And here we have the Bluetooth version number of the BM788BT. So after I played around for a few minutes, I can actually tell you there's another feature which is not very obvious. That is actually you can plot the current reading versus time. So let's take a look at here. So if you go to the dashboard, you can see here we have to select the device and you select the channel. So once you select it, you can see here, we can now enable the real-time logger. So once you enable the real-time logger, I know there's just so many steps, but once you enable that, you can actually start. And here you can choose the different modes. So basically the difference between the eco and power is actually the eco mode, it updates slower, and the power mode, it just updates more frequent. So let's actually choose the power mode. And you can see, hopefully, that it starts to plot the current voltage reading as seen on the BM788BT. So let's actually hook up a signal and we take a look. So right now I'm just using the signal generator to generate a 100 millihertz sinusoidal. You can see that the voltage waveform is measured and captured by the phone app. Very neat. So that's the Bluetooth connectivity. I think it's definitely very useful, but the functionality provided by the phone app is quite limited. This meter also has the auto hold functionality, and that is very useful, especially if you're trying to make some delicate measurements that require your full attention. You can't just kind of look at your measurement and then look at the meter. You really have to pay attention. And in this case, you can use this mode to automatically hold the value when the reading is stable. Let me show you that here. For the demonstration, let's actually change to DC measurement mode. And let's enable auto hold. And let's measure the battery. So you heard it beep, and when it beeps, it means it already detected a stable reading, and you can see here, the voltage is displayed, and I'm not measuring the battery here. So that gives you the last stable reading. And of course, if I change a different battery, remember the reading here, and it should Yep, measure a different reading, and now I can put the battery away, and it will still hold that value. And this is definitely very useful in real-world measurements, because you can have your full attention on the circuit you're doing measurement with, and then the meter will beep and tell you a stable reading has been achieved. You can use this feature for component binning as well. Now let's take a look at the DC measurement range accuracy. First, let's take a look at the millivolt range. For that, I'm using my EDC MV2168 voltage standard. And currently the output is at 0. You can see that we have a 0.01 millivolt or 10 microvolts offset. So to verify the resolution of the meter, I'm going to increment the voltage standard output 10 microvolt at a time. So let's do that. 10 microvolt, 20, 30, 40, 50, 60, 70, 80, 90, and we have 100 microvolts. And you can see that, except for the last digit, everything else works out great. Now let's do it 1 millivolt at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No issues. 10 at a time. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. No issues. All right, let's do 0.1 volt at a time. 0.1, 2, 3, 4, 5, 6, and I think we're going to overrange here, 7. Yep, because it's in millivolt range. Okay, so very good. Now let's change it to volt range. And we're currently measuring DC volt. So let's do 0.1 at a time. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1 volt. You can see that essentially it's spot on. All right, let's do 1 volt at a time. 1, 2, 3, 4, 5, 6, 7, and we're losing a digit because this is a 60,000 counts meter. 8, 9, 10. Excellent. Now let me quickly demonstrate a couple of functions I forgot to mention. The first is this crest function. Crest function allows you to measure the peak value of either voltage or current with short duration. So right now you can see on the function generator, we're generating a waveform that is square wave with an amplitude of 2 volts peak to peak and offset of 1 volt. So basically the entire waveform is between 0 and 2 volts. And the frequency is 1 hertz. So you can see the voltage measurement is jumping around. If we enable the crest, let's see what happens. So let's press crest. You can see that it recorded the maximum voltage is around 2 volts. And we can press this. You can see the minimum voltage is right around 0 volts. So that's exactly what we're outputting here. So essentially we can use the crest function to measure the peak of the signal within a short duration. The bar graph on this Brymen updates up to 50 times per second, which makes it suitable for indicating rapidly changing signals. A lot of the cheap meters I reviewed have bar graphs, but they update at the same speed as the main display, which makes the bar graph far less useful. Right now the function generator is outputting a 1 Hz signal. You can see that from both the display and also the bar graph. Of course, I'm going to increase the frequency and you can see the display and also the update of the bar graph here. So let's increase it 2 Hz, 3, 4, and you can see that at 4 Hz, of course, you can still see the update on the display, but you can't figure out what exactly is happening. But the bar graph actually tells you that. Now let's do 5, 6, 7. You can see the bar graph update rate is really fast. So through the bar graph, you can actually have an idea of what signal you're currently viewing. And let me reduce the frequency here. So let's do 5 Hz. So now you can see how useful it is to have a fast updating bar graph. From the displaying digit alone, you can't really tell what is happening. But from the bar graph, you can actually see the signal is changing between 0 and the maximum value. Now let's take a look at the record button. And the signal generator right now is outputting a sinusoidal between 0 and 5 volts. You can see it is changing on the display here. What this record does is it records an interval of the signal, whether or not it's voltage or current. And it will tell you the minimum, maximum, and also the average within that interval. So now let's give it a try. And every time it's beeping, it's actually detecting a new high or new low. Let's actually press it again, and we'll see what is a captured high. This is the high value, you can see maximum, and the low, that is the min. And if it's updating, you can start beeping. Yep, you can see that it just updated a new min value. And let's see the average. Because the waveform is still continuing, and you can see the average is changing. So that's how this min, max, and average works. And that is done via this record button. Of course, when you're done, you can just press and hold, and you'll get back to the measurement. When I was showing the frequency measurement earlier, I forgot to mention that it can also measure duty cycle. So now, for example, we have this pulse signal at 1 kHz and with a duty cycle of 10%. So let's take a quick look. So now we're in the millivolts range. You can see I switched to the frequency measurement, and it's showing 1 kHz, which is exactly the same frequency as we're outputting. And let's press it again. You can see that currently the duty cycle is 9.99, and we are here at 10%. So if I change the duty cycle here, 20%, and you can see that we can measure that with no problem. So this is the functionality I forgot to mention. Next, let's take a look at the resistance measurement mode. And in this mode, we actually have two measurement types. One is to measure resistance, which we can measure up to 60 megohms. The other is to measure conductance, which we can measure up to 100 nanosiemens, which covers between roughly 100K and well into the gigohm range. So now let's actually start with the resistor. Let's first short out the leads. And you can see that it's actually relatively fast. So let's zero it out. And the first one we're going to measure is this 100 ohm precision resistor is 0.1%. You can see that no problem. And the measurement speed is relatively fast. And the next one we're going to measure is this 1.25K 1% tolerance resistor. And you can see, again, the measurement is pretty fast. And we get the reading right in the ballpark. The next one is I think this is a 10K resistor. Can't really see from here. Let's see. Yep, it's 10K. And the next one is a 4.7K. Let's see here. Yep, 4.7K. And let's try a 1 megohm resistor. And you can see that the measurement speed is very fast. For resistance higher than 60 megohms, you can't use the resistance mode to measure that. For example, here is a 100 megohm resistor, and you can see that we can't really get any results. Now, we can actually use the UNI-T UT61E Plus to measure this resistor. Give me 1 second. So here, the same resistor with the UNI-T. Let's see. And you can see we're actually getting a reading. But anyway, so this is a 100 megohm resistor. This is where the conductance mode comes in handy. Let's switch to that. And you can see the result is in nanosiemens. And we're measuring roughly 10 nanosiemens. So that's roughly 100 megohms. So the lowest reading you can see is 0.01 nanosiemens, which translates into 100 gigohms. But we don't have much resolution here because a reading of 0.02 translates into 50 gigohms. This means that if you want to use this meter to infer high resistance, you probably aren't going to be able to do that accurately up to about 10 gigohms. And now let's take a look at continuity. So let's press it again. And it's very fast, but it's a little bit scratchy, so I don't think the measurement is latched. But that shouldn't be a problem, as it's really fast here. I actually don't mind this at all. Now let's take a look at the capacitance measurement mode. And this is probably the only disappointment so far, is that in the capacitance mode, you can see here, the minimum resolution is only 10 picofarads, which means I really can't use that to accurately measure small capacitance. Here I have a 33 picofarads capacitor. Let's give it a try. Of course, we have some residual. Let's zero it out. And let's see here. So you can see the result is actually correct. It's 0.04. We're measuring 33 picofarads capacitor, so that's roughly correct. Unfortunately, we just don't have the resolution here. Next, let's measure a 100 nanofarads capacitor. And this is right around the ballpark for this capacitor. Now let's take a look at the 1 microfarad capacitor. And again, it is pretty close. So now let's take a look at this 820 microfarads capacitor. No problem. According to the spec, the largest capacitor you can measure is up to 10 millifarads. Now, this capacitor I've been using for all the meters is actually 15 millifarads. So this is obviously above the maximum specification. But let's actually take a look to see if we can measure this. Yeah, you can see that actually it was able to measure the capacitance. The result is actually consistent with the ones measured by other meters. So the capacitance measurement actually is pretty accurate, but the range is relatively limited compared to the other meters I have. That's the only downside so far for this BM788BT. All right, now let's take a look at the diode measurement. And for diode, let's see if we short the leads. Yeah, very good. It will tell you that actually is a bad PN junction, you can see here. So let's see if it beeps when we have a good PN junction. So let's do a signal diode here. Yep, very good. You can see that it gives a short beep, indicating it's a good diode, and the forward voltage is 0.7 volts. Sorry, it's not in contact here. So let's take a look at another one. This is a red LED. Yeah, you don't get that beeping anymore because I think for a PN junction, it's typically between 0.2 and 0.8 volts. And that's for silicon diode. Of course, this is an LED, so it doesn't really count. You can see that the LED is actually lit. Not sure if you can see that on camera, but it's not very bright. Let's try a different LED. This is a white LED. Okay, you can see it lighting up, no problem. And also we're able to measure the forward voltage drop. The BM788BT also supports temperature measurement. Not only does it support that, it actually supports 2 thermocouples to be used simultaneously. And this is the supplied thermocouple, and you can see it's a very high quality one. So let's actually use the second thermocouple connection here so that we can still connect the probes while using the thermocouple. Of course, right now we're in the wrong range. That's why it's beeping. So let's change it to the thermocouple mode. Of course, right now it's trying to measure T1. We don't have this thermocouple plugged in. So let's actually change it to T2. So you can see this is the temperature of the lab. And if I put my hands on it, of course, it will change. Very good. So let me find another thermocouple and plug it into the T1 position. All right, I have another thermocouple here. And you can see this is also a K-type thermocouple, so let me plug it here. So now we can switch between 1 and 2. Let's see, this is T1, and this is T2. Of course, there is some temperature difference. Of course, you can actually do the calculation right here. T1 minus T2 is 3 degrees Fahrenheit. Very good. Now let's take a look at the current measurement. For that, I have put the BM788BT and the UNI-T UT8806 in series. Currently, I'm using the microamp range on the BM788BT, and I want to measure this 100 microamps current standard. So let's give it a try. And you can see on the BM788BT, we're spot on. Of course, we're actually pretty much spot on the UNI-T as well. And here we're measuring 100 milliamps. Let's change it to 200, 300, 4, 5, 6, 7, 8, 9, and 1 amp. No problem. The burden voltage on the BM788BT is actually very low in the amp range. So now let's take a look. Right now we're measuring 1 amp spot on, and let's see what the burden voltage is. So for that, you can see here, this is our amp input, and I'm going to see what the burden voltage is on the UNI-T here. So you can see we're roughly measuring 51, 52 millivolts, and that's the burden voltage per amp in the amp range. Another unique feature of the BM788BT is that it can actually measure the loop current percentage. On the left, I have a tool-top ET75 process meter, and it's currently outputting 4 milliamps. And you can see that we're measuring exactly 4 milliamps on the BM788BT. But it has an additional feature here. The BM788BT actually does the conversion for you automatically. So let's take a look. So I'm going to press select again. And you can see here, right now we're showing 0, that's 0%. And watch what happens if I increase the current here. So if I go up, and it will actually map the current reading into the percentage between 4 and 20 milliamps. So you can see that. So this is actually very convenient. So let's go up to 12. And you can see here, that is 50%. So if I go up to 20 milliamps, it should be 100%. Here we go. Of course, you don't have to use this function. You could just come back here and read the current yourself, but then you have to do the calculation by yourself as well. All right, I think I have demonstrated pretty much all the functionalities this meter has to offer. There might be a few I left out unintentionally, but you get the gist of it. Now let's open it up and take a quick peek inside. Now, when Brymen says it's Cat 3 and Cat 4 rated, you better believe it. Now I just took out the battery compartment. You can see it's actually a very unique design here. We have 3 of these AAA batteries, and essentially they are mounted vertically down into the case. And it is connected by these 2 contacts here. Because the battery connections here are actually hard to get to, and there's not an easy way for me to connect an external power supply. So I'm not going to measure the power consumption, but according to the manual, it's right around between 8 to 10 milliamps. So that's actually quite minimal. With all these 6 screws loosened, we should be able to open it up. But before I do that, I want to show you we have this programming header, and this is actually used for factory to program the firmware after the unit has been assembled. Anyway, let's open it up. There's not a whole lot going on the cover here. Everything is on the bottom side. Wow, this is absolutely beautiful. You can see here, this is the big fuse for the 10 amp range. That's a HBC fuse. And here we have a smaller fuse that is for the lower current range. And from here, you can see we have a current shunt. These are the 4 split jackets. We can probably take a look later on the other side. And here we have 2 PTCs and 3 big MOVs. All right, I just removed the board off the camera, and there are 4 screws actually screwed into the bottom of the case. You can see here are the 4 screw holes, 1, 2, 3, 4, and the case itself has the shielding material at the bottom. I have also removed the LCD assembly from the main board. The LCD is essentially plugged in to the main board via these headers here. And also there are 5 screws at the back secured onto the main board. Anyway, there's not too much going on with the LCD. And on the main board here, you can see we have this Bluetooth module. So let me actually see if I can remove it. Yeah, I think these are just mounted with the headers. So let me try to remove it. So this should be just your off-the-shelf Bluetooth modules, I guess. So let's take a quick look. And you can see here, these are the 4 jacks. These are split socket jacks. And if you look back here, you can see that we actually have 2 connectors per jack. And that's because these 2 sides are not connected. And I think some of the soldering is probably done by hand. You can see here and here. Now, this is understandable. And this kind of board, typically, you have certain components have to be done by hand. And you can see the board itself is actually very densely populated. And they have to cram in a lot of circuitry into this tiny board. So the designers must have taken a lot of consideration in. For example, this is your high precision divider resistor. And of course, it's mounted at an angle because there's not enough space to do it horizontally. Anyway, so those are some of the design considerations. You can see that the layout is absolutely beautiful. Now up here we have this chip. I don't know what it is because this part number I can't find anything on the internet. I assume the part number probably is Brymen specific. And throughout the board you can see a lot of these isolation slots. Designers clearly had put a lot of thoughts into that. And on this side you can probably see on the silk screen here, we have 786, 787, 788, 789 BT, and all these models probably use very similar board and probably have certain components omitted in certain models. And this one is a 788 BT. If you turn it around, you can see that we actually have this marked on the board right here. On this side of the board, you can see it's pretty cramped, and that's because we have all these larger components. And this larger one here, that is a fusible resistor. From the layout and also all the protection circuitry here, you can absolutely tell that this is from a name brand rather than a no-name brand multimeter. Everything here the designer has put a lot of thought in. For example, we have 2 of these different sized PTCs, and we have 3 very large MOVs, and these help to absorb transients. And here's a current shunt for the 10 amps range. Then up here, that's our digital multimeter section. Now the multimeter section is actually shielded, and the shielding is actually soldered onto the board. I don't think I'm going to desolder this shielding can. The reason is you can see here, this is soldered at this point and multiple points here. And we also have this plastic shield on top. So I'm not going to try to desolder it because I think I'm going to damage the board. But if you look at an angle, you can kind of see this oscillator here. And further down, you can kind of see that chip there. And that's the DMM chip. Another reason I don't want to remove the shielding is because I know that I probably won't tell which DMM chip they're using here. Anyway, we also have a few trim pots for calibration. And down here, that's our display driver. And here, by the look of it, that's a TLV233. I think that's an op-amp. And here, that's a 4053. That's a MUX. Let's see what else. And I think that's pretty much it. Yeah, you can see also we have this physical isolation barrier. Very nice. So the only thing I would say is that I don't know the long-term reliability of these split jacks. But I have had my 2709B, that one also uses similar design, for a long time now. And that meter had never had any issues. Of course, there was one time I did need to resolder some of the jacks because I think over time it had come loose. But other than that, I don't think I had any other issues. So anyway, so that's the only part we have to find out in the long term. The BM788BT is precise, has high resolution, is feature-rich, and is well-engineered. You really can't ask much more than that for a multimeter. For those who are interested in this meter, please check out Alishop's link in the video description below. And if you are in the United States, you probably don't want to import yourself as an individual, as it will be much more expensive. This meter can be found on reputable sellers in the United States for around $300 shipped. I really like this meter. The only thing is that the capacitance range is a little bit limited. But besides that, I think it's a great meter, and I will be using this meter as my daily meter for the foreseeable future. And I will let you know how well it works in the long term. I hope you enjoyed today's video. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.